Hey class, how's it going? It is currently Friday when I am recording this review, so I had a very nice, enjoyable um, break. So that being said, let's go ahead and jump back into chemistry. Let's get some of this stuff reviewed, and we'll go over some topics that may have been missed if you happen to miss one of the labs, or if I just wasn't explaining it good enough. And if that's the case, that I wasn't explaining it good enough, you can always look it up on, I think Crash Course might have a few videos. I'll make sure to link them in the description of this video because it should be on YouTube if I can figure out how to do that correctly. And yes, that is my YouTube channel. Do not subscribe to it, please. Because if I am going to post any videos there, I'm probably going to regret it like 3 months down the line. So it's not like there's anything that will be worth watching besides this review. So anyway, let's go ahead and get started. What we're going to be working with first, before we jump into any of the labs, is two concepts that may have been missed like throughout the entire semester, and something that will be very important to remember going forward. The first one being labeling our units, and the second being percent error. So let me write those down real quick. Believe it or not, this is actually the second time that I am doing this review. The first time, I thought everything was going to be backwards, so I wrote backwards. Turns out that the camera flips it for me, so I was just writing backwards for no reason. Yeah, a total blonde moment there. So I said labeling units and percent error. So the big reason why labeling units is so important and why you should get into the practice of actually doing it is when you get into our labs, the gas laws and the heat and enthalpy changes, there are very specific units that we're using in those equations that will help you solve for the rest of your problems and how to set them up. That being said, when you label your units, it's really a simple thing. You're just keeping track of what your suffixes and prefixes are. So if you're working with meters and you want it to be like a little bit bigger, you're going to go with kilometers. If you want to work with it something smaller, you go for millimeters. Biggest reason is that if you don't tell someone what you're measuring in, they won't know what you're talking about. So in at least how I've been viewing it is that I sort of know what you're talking about in lab because you've done the work. You can verbalize to me that this is the way that you're thinking. It's just that the units may be a little bit weird for you. However, moving forward, you gotta break out of the habit. It's very beneficial to keep those things at the end because one, when you get to the bigger equations, like bigger than the stuff that we've been working on in lab, you're going to have to deal with keeping track of your units. If you're planning on taking physics, units is a very big part of that because if any of you have looked into physics or done physics in high school, you'll know that breaking down Newton's, I think, I can't even remember. It's been years since I've taken physics now, but there are certain units that you do have to break down into their different increments. Like that's the one I was thinking about. Joules. It was like kilograms meters squared divided by seconds squared, something like that. So anyway, before I start rambling on about all the stuff that you probably should know, just remember you need to start labeling your units, and if you have been doing that already, good, keep doing it, don't give up on them. It's very important, especially if you're trying to convey this information to someone else. When you're doing an exam, you're trying to show Dr. Patel, Mr. Hinton, that you know these things so much so that you can write them down and have the units there to kind of express to them. You know what I mean? Anyway, let's move on to percent error. So percent error, we've been working with it all semester. Let me go ahead and write down the equation for you. Reason why this is going to be very important for you to remember is that if you don't keep track of it, at least the proper way to do it, you could end up losing points on something that is actually relatively easy, something that you can practice on and off, even with stuff at home, like cooking or, you know, seeing how much soap that you use, like to wash your hands. It's an excessive way to think about it, but you can use this in like an everyday scheme or even practice it in an everyday scheme. Because, I mean, even though I teach you guys chemistry, I'm not looking for the percent error of the weight of oats that I put into my morning oats. You know what I mean? So anyway, minus actual divided by actual times 100%. And that's where those units come in. And just so you know, I am writing on a whiteboard. I'm not just writing on something in my lap. I mean, I am, but it's this. This is your equation that you're going to want to use. Your tested is whatever value that you measured. It was like, say for our gas laws, if you tracked a certain pressure, then you did the calculations to find that pressure. That's your tested. Your actual is when all of your things are supposed to align correctly, and that is like absolute perfect, like 100% yield that you're getting. And of course, since life is tricky, and so is science and chemistry, you're not always going to get 100% yield. So that's why we use this equation to know how much we're actually working with. Because I mean, I'll tell you, working for ACTS and doing like the outreach events, it's absolutely necessary for me to keep track of how much product that I'm making if I'm trying to take that product and put it into another experiment. A good example to use there is elephant's toothpaste. If I am going to start with a Lattice lamp, which is it's a water vapor demonstration where I put potassium iodide into hydrogen peroxide, a very high concentration of hydrogen peroxide, it should start to bubble and smoke. The smoke isn't actual like carbon smoke, it's just water vapor and a lot of heat. So when it's doing that, it's going to have some leftover in there of whatever chemical, and most often it's going to be the potassium iodide because now it's in like water. Well, when I go to add more hydrogen peroxide and soap to make elephant's toothpaste, I can still use that same product to create another experiment, if that makes sense. So it's important to know how much product you'll be dealing with and how much you'll be like losing. So at least for that one, if I was to do like a percent yield equation or tracking a percent error, I know that I am within a certain bounds that I can still use the potassium iodide in that experiment because it's not going to go anywhere. And if it is, it's a very small amount into the atmosphere. And if you hear dogs, I have dogs. This guy is Thanos. I'm not going to pick him up because he's going to kick the computer. Anyway, enough about dogs. Let's move on to Lab 9 because I know that this video is getting long already. So I mean, this is probably going to be a long one. I'll try to make some markers in there so that you know where to go and what to track when it comes to the review. So Lab 9 was gas laws. That's where we worked with the Pivner equation, and we tracked some pressures, tried to not blow up those microlab boxes, whatever else. When it comes to pressures, it's really important to note that typically whenever you have a set volume and you put more pressure on it, more oftentimes you're going to build heat. If you want to think of it this way, like dinosaurs, they're turned into fossil fuels. So if you have this collection of organic matter, you put a lot of pressure and heat on it, it's going to turn into a rock. Now that isn't in all cases, but for just a brief like understanding of it, if you're going to put pressure on something, more oftentimes you're going to raise the temperature if everything else is perfectly the same. Now, you're of course going to decrease the volume. That's going to be a big part of it. But anyway, so I don't blabber on too long, we're looking at the relationship first between pressure and volume. When you try to decrease the volume and there's a set amount in there, you're going to raise the pressure because now there is less room for all those molecules to go, and you're tracking the pressure as something that is super condensed. If you need like a really small way to think about it, it's like if you're gonna like clasp your hands together, that's an okay pressure. If you try to squeeze your hand, you're now building pressure. There's less room for your hand to sit in, so if you really need to think about it that way, more pressure, less space. Think about it the other way. If you have less, or you have more volume, you have less pressure. So say I'm holding my hand here, there's a little bit of pressure, it's a very gentle pressure, but now I'm going to take my hand away, and now there's more volume, there's less pressure on my hand. Of course, I can't go too far because I am surrounded by air. There's still going to be constant pressure, but you can expect that as you get further and further away, you start to create a vacuum where stuff is trying to be sucked back in because it's trying to get back to that same atmospheric pressure as everything else. So, moving on from our pressure and volume sort of relationships, let's talk about the measurement for absolute zero. absolute zero is actually 0 Kelvin. That being said, absolute zero is the temperature at which molecules stop moving. That's what people theorize as the heat death of the universe, when all molecules cease to exist, and you could think of it as like a scary thing. Really, it's just a phenomenon that we can't even really get to. We've tried to get close to it, but the perfect absolute zero just hasn't been attained yet. For this experiment, though, for part 2, what we were trying to do was we were trying to get something to absolute zero, or we were trying to track a trend line. From what we saw, that trend line was linear, and as we went down this linear slope and we were trying to get to that absolute zero, we found that the pressure couldn't actually reach a zero pressure. Of course, that could have been because of human error, calculations, whatnot. There may be extra phenomena that we don't know about, but pulling the distinction between 0 Kelvin and 0 degrees Celsius, 0 Kelvin is your true absolute zero. 0 Celsius is the temperature at which water freezes. Of course, 100 degrees being the boiling point, 0 degrees is our freezing point, and then when you jump to 0 K, that is our absolute zero. Now that I've sort of hammered through that a little bit, let's talk about our Pivner equation, and let's actually break it down, and I'll show you a few tricks that you can use to actually work with the rest of your equation. So Pivner, we got our pressure, our volume, our moles, our specific atmospheric value, and then our temperature. I can't see where the actual, I guess it's just called our R value. I'll just call it the R value. I like to call it specific heat. That's not actually what it is. So breaking this down, our pressure is typically going to be in ATMs, torrs, or millimeters of mercury. We'll get to why we used millimeters of water in the lab. And then we have our volume, which could be measured in liters, centimeters cubed, milliliters, any of those. Our N is our moles. Of course, you can only measure that as moles. If you try to put grams in there, you're going to mess with the equation. And then your R value, which we'll talk about, is the key to the rest of your equation here. And then your temperature, which will typically be in degrees Celsius. Excuse me. I just had breakfast, sorry. And yeah, so let's go ahead and break all that down. So we'll start with our R value, right? Our R value is going to be the key to the rest of our equation. Reason being, it has all of the units that you're going to use. More oftentimes, if you look to your R value, you know what your other variables are supposed to be in. So I'm going to cut this off here until I can find my R value example that I can use. Cutting back in, I finally found the value that I'm going to be using. So my R value for this, what we should have seen in the lab, was liters times atmospheres divided by moles times Kelvin. The biggest thing, if you have anything that's on the top, you can expect that to be on the other side of our equation. Anything that's on the bottom should be on this side. Reason being, when you try to solve this so that R is by itself, you're going to take this N and T and you're going to divide it over. That way, you sort of end up with the same equation anyway. So when I'm doing the math for this, if I have my volume in milliliters, I'm going to want to convert it to liters. So I'll go ahead and just divide that by 1,000. Bam, I got my liters. If I've got a pressure and I'm stuck with like 760 millimeters of mercury, I know that that can convert into 1 atmosphere perfectly. So I'll just flip those over. Now I have my atmospheres. However, my moles, that may come with a little bit extra work, because now that you've done labs 9, 10, and 11, you should have been able to collect how much gas is contained in a certain volume. So of course, if you have 1 mole of a gas, it takes up 22.4 liters of space. However you want to sort through that, really you could probably just take the mass and work through it that way. But for this case, I'm going to go ahead and show you how to find your moles from your liters of gas. So let's go ahead and solve for N. I'm going to reshape this top equation so that I can find my N value. So I'll have N equals PV over RT. So that's the equation that I want to work with so that I can get my moles. So here it says that I'm working with 1.356 ATM, and it's important to keep a certain number of numbers after the value because that can really change your really small value of moles in the end. Let's see, multiply this by my volume, which is 0.024 liters. I'll divide that all by my R value, which is 0.08206, and I'm just going to draw an arrow from what my unit is. And then I'm going to use Kelvin for this case because that's what it's calling for. More oftentimes, you're just going to want to use Kelvin. It's easier for this equation. Always look for your R value and what that's stating for you so that you can plug in the right temperature. So this is the equation that I have to figure out my moles. I've plugged in my ATMs, my liters. This is my R value. Of course, it should be constant. And then my 294 Kelvin. That is my temperature converted by adding 273 to whatever degrees Celsius I had. Still works even if you have a negative Celsius. You can still add that Kelvin on top of it, and it should give you the correct number. Solving all this through using a calculator, you're going to want to make sure to split these up into their individual parts. So really, if I was to think about it, I would have a pair of parentheses on the top and a pair of parentheses on the bottom. There's probably a math reason why you could probably do it the other way, but this way you know that you're going to get the correct answer every time. So I'm going to go ahead and solve the top first, and then solve the bottom second, and then I'll do the rest of the equation. That should give me my moles. In this case, I had 1.3489 times 10 to the minus 3 moles. So I have that now. I can now take that measurement of moles and turn it into other equations that I might need. So in the case of I want to find how many molecules of a gas, if I want to find out how heavy the gas is, I can look to the actual equation of that gas, and then I can solve through with that. So moving on, that is about the last part of this, a important sort of relationship to remember when it comes to pressures, and this will be the last thing that I talk about for this lab. So because of the system that we were working with to find our gas collection tube, we can find the pressure of hydrogen by moving around some values. So we can assume that if we want the pressure of hydrogen inside that tube, right, we have several values that are acting on it. So just to show you that I'm keeping track, that pressure of the hydrogen inside the tube is trying to build up and push everything out. When it comes to the other pressures that are acting on the system, we have the pressure of the atmosphere that is working directly against us because we did have it submerged in a beaker. That pressure is trying to push down on the water level to push the water inside of the tube. Of course, as laws of thermodynamics dictate, we want to have an equal pressure. So what it's trying to do is it's trying to reach that equilibrium inside the tube so that both the water level of the beaker and the water level of the burette are about the same. If not, it's going to push it up just a little bit higher because of extra pressures. The next part that we want to worry about is the pressure of water vapor, which was a bit complicating to understand, at least for me. So I'm going to attach a video to this so that you can sort of understand a bit better how to work with the pressure of water vapor in your equations. And then lastly is your pressure with the height of water. So to do a quick sort of overview of how that works, we'll do my burette in water. We'll say this is my water level, and that's my water in the burette. So here, my water level is pretty high in the burette. My water level in the beaker is fine. It's where it should be sitting. So what I can assume from this relation is that the pressure outside of this has decided to push the water into the tube until it has reached a specific value that both pressures are equal. So in this small area here, we have pressure that is 1 atm, if the outside is going to be 1 atm. That being the case, we can see that this pressure here is pushing up on that, and the water may also, this difference of water here, may also be pushing up on that as well. So let me go ahead and write down my other values in there. My pressure of atmospheres minus my pressure of water vapor. And then I'm also going to subtract in my pressure of water height. Now, a quick thing to note when you're working with the height of water to track a pressure. Mercury, which we've used before in pressures, is if 1 atm is 760 millimeters of mercury, you can expect that that is the distance that mercury is taking up to have 1 atmosphere. Now, for this case, we're working with water. Water is not mercury. Mercury, in fact, is 13.6 times denser than water. So what we're going to want to do is, once we've found the height of our water in millimeters, because if we want to convert over, it's easy to keep it in those units. We'll say I've got, just to make it easy, I got 13.6 millimeters of water, and I'll abbreviate that as H2O. I'm going to take my ratio of 13.6, which is just going to say that we're converting our mercury, or we're converting our water into mercury. So I'll say, if I'm dividing by that, I'll say it's H2O on the top, and then mercury on the bottom. Now this is like an old algebra trick, just to make sure to have you guys knowing. This, I know, is going to be the value that is going to cancel this. If this is on the bottom, I know that is, I divide this in, it's going to flip, and that's going to become my new value. Now, I know that was kind of weird to say. So, algebra standards, this is going to divide into this, because these are both on the top, I guess you could say. If you think about the top H2O, I'll rewrite it like this. My H2O divided by a value. So having it this way, I can see that this bottom one, the 1 just means that it's an empty value. By dividing this through, I can get rid of both H2Os, which will leave me with my mercury, but because I'm dividing a divider, an easy way that I like to think of this is, since my slash is a divide, like I'm dividing something through, I can put 2 divides together, and now it's a multiply. I know that sounds really dumb, but it's helped me with a lot of math. So at the very end, I'm going to have 1 millimeter of mercury that is going to be acting on top of this. Now that you have like all those values for pressure, the next thing that you're going to need to do is convert those into a single unit that you can just subtract into each other. Because you can't do multiplication, because it is a subtraction equation, all of those units need to be the same. There's probably a math value or some concept out there that I don't know the name of, but if you're going to do something like that, you need to have the same units. So like I said, when we had our millimeters of mercury, if you're using ATMs for your pressure of hydrogen, you need to convert that into the atmospheres, if that makes sense. So that is Lab 9, gas laws. Let's go ahead and move on to Lab 10. I will probably put that in a separate video so that you guys have little chunks, because this is already 26 minutes long, and I don't know how long it's going to take to upload. So be safe, don't do anything that I wouldn't do, and make sure to wear your lab coats and your shoes whenever you're working with chemicals.